Okay, I want to talk a little bit about composition of functions. It's covered in section 1.3 in our e-text, and there is some homework with this topic. Should be a review for you, so I'm throwing it in with the prerequisite material. There's some extra practice as well in the prerequisite homework. At any rate, when we talk about the composition of two functions, we sometimes will say f composed with g, where f and g are two functions, or the composition of f with g. And the way it's written is this way. You should remember this notation. That little circle is not the letter O, but it's a little circle. F circle G is the way this is actually said. F circle G is the composition of F with G. And the definition is that it's F of G of X. The idea is you're evaluating the function G, right? You plug in X and you get the output G of X. You get that output and you plug that value into the function F. We sometimes call G of X the inner function and the function F the outer function in that case. So the idea is you can think of the function G as the inner function. It's like a black box, right? We plug X into the function. Whatever the rule is, we get an output, right? You plug in X, you output what? G of X. Then we take that output G of X and we plug it into the function F, and out comes F of G of X. That's F circle G of X, the composition of F with G of X. So let's just look at examples. This should be familiar to you. If F of X is x squared plus 3x minus 2 and G of X is this function, let's find F circle G of X, and let's find G circle F of X, because we'll see when you change the order, when you change the outer and inner function, swap them, you in general will get different results. So for example, if I do F circle G of X, right? F circle G of X by definition is F of G of X. So I take the function G of X. What is that? That's the function 5x minus 1. Right? That's the output. If I plug X into the function G, the output is 5x minus 1. And now I'm going to take that 5x minus 1, that output to the function G, and I'm going to plug it into the function F. Here's the function F. Wherever I see an X, right, I'm going to replace it with what's inside here. So whatever is inside here, which is 5x minus 1, I'm going to first square that whole quantity, 5x minus 1 squared, and then 3 times that quantity, 3 times that quantity. And then don't forget the minus 2. So that is F of G of X. But you should go ahead and do the simplification. And when you square 5x minus 1, very important to realize that that is not 25x squared and then squaring -1 plus 1. You can't do that, right? Remember that this 5x minus 1 squared is this, right? So you have to, FOIL that out, or if you remember the special product for a perfect square trinomial, you should be able to get then that this is 25x squared minus 10x, because that's the outer and the inner are both -5x, and then plus 1, right? -1 times -1 is plus 1. So it's not 25x squared plus 1 or 25x squared minus 1 when you square 5x minus 1. You've got to make sure you're careful with your algebra. Here I just distribute the 3 through, I get 15x minus 3. Now I can combine like terms, and there's F circle G of X. Well, what about G circle F of X? Well, that is by definition G of F of X. Well, now we're going to plug the function F of X. So remember, this is the rule for F of X, x squared plus 3x minus 2. I plug that into the function G. So remember, the function G was just whatever you plug in, you multiply by 5 and you subtract 1. So this is fairly easy here. We take all this, multiply it by 5, and then we're going to subtract 1. Distributing the 5 through gives me this. Combining the like terms gives me that. You can see that F of G of X, F circle G of X up here is not the same as g circle f of x. So they are different. Okay, so that's the basic idea. Now there's lots of different functions we can compose together and create these compositions. So here's another set, another example here. So I've actually already done these, but if the function f is sine of x and the function g of x is x cubed plus 4x, what is f circle g of x, right? So again, this would be f of g of x, right? Well, g of x is just this stuff, x cubed plus 4x. And then I take this stuff and plug it into this function, which means I just take the sine of all this stuff. It's real important when you're dealing with functions. This is the sine function. This is not sine times x cubed plus 4x. This is sine of x cubed plus 4x. So you can't distribute and say this is sine of x cubed plus sine of 4x, right? This is sine of the quantity x cubed plus 4x. In other words, you'd have to evaluate what x cubed plus 4x was first, and then get that value and take the sine of that value. What about g circle f of x? Well, that's going to be g of f of x is sine of x. So I go to the function g of x here, right? Whatever I plug in, I'm going to cube it, multiply it by 4, and then add. So I'm going to cube sine, and then I'm going to multiply sine by 4. Now, when we cube sine, how do we usually write sine of x cubed? Well, you should be familiar with this notation, sine cubed x. That's what we mean when we write sine cubed of x. It's really sine of x cubed. It's not sine of x cubed, right? So this right here is not the same as if I write sine of x cubed. So notice the parentheses is real important here. You know, it's cubing x first and then taking the sine, which is not what we're doing here. We're taking the sine first and then cubing it. So this is the composition. And again, you can see the difference between changing the order that we compose with, not the same thing. These are not the same thing. What about this? F of g of f of x. We can keep composing functions. In other words, you can even take a function, take its output and plug it back into the original function. There's actually a lot of application where we would do that. And so in calculus, we might encounter the composition of 3 or more functions sometimes. We'll see later on. So what is this? Well, we just calculated g of f of x actually inside here, right? That's what we're plugging into the function f. G of f of x is right here. This right here is g of f of x. So this will be f of what? Sine cubed x plus 4 sine of x. And what is f of x again? F of x was just sine of x. So I'm going to take the sine of all this stuff. Okay. So sometimes we're composing functions in different ways and you get some weird looking stuff. I mean, this is just a weird looking function. It's real important you understand the difference here. The input to the sine function is everything in the parentheses here. Right, so this is the sine of all this stuff. Again, it's not multiplying. It's not sin, which by itself is, of course, a sin. We don't want to do that, right? You have to have something going into the sine function. It's all this stuff. And you have to first, inside here, right, find the value of sine of x, cube it, multiply the value of sine of x by 4, add those two things, and then take that number, plug it into the sine function again, and get an output. So we get a lot of these nested situations there. Let's quickly look at a few others. So p of x is e to the x, exponential function with base e, right? Or the natural exponential function, and m of x is the tangent function, right? Tangent of x. So what's p circle m of x, right? That's p of m of x. Well, m of x is just the function tangent x, right? So I'm going to plug that output tangent x into the function here. And notice this function, whatever we plug in, becomes the exponent on the base e. Remember, e is a number, fixed number. It's about 2.718. That's the natural base, or Euler's number. And so this becomes e to the tangent of x. And we'll be dealing with expressions like that later on in calculus. This is not MOP. It's not MOP. It looks like it's M circle P, right? It's M of P of x. And here P of x is, in this case, e to the x. And so I take e to the x, plug it in here, I get tangent of e to the x. I would prefer to write it that way, emphasizing that we don't have to have the parentheses here. A lot of times we drop that, but it's important to realize this is tangent of e to the x and not tangent x times e to the x. But again, you can see when we compose differently, we get different outputs. What if h of x was x to the fifth and we asked for m of p of h of x? So here's a composition of 3 functions, and we can continue to do this. I mean, you could have 5 functions composed together. What will this be? Well, this is m of p of x to the fifth, right? H of x being x to the fifth. What's p of x to the fifth? So again, we're going to work innermost parentheses first and work our way out. So I've got to figure out what this is first, p of x to the fifth. Well, again, p of x is e to the x, so I'm replacing x with x to the fifth. So this becomes e x to the fifth. So this is m of e x to the fifth, which is tangent of e to the x to the fifth power. Okay, composition of 3 functions. Just want to say a little side note, had nothing really to do with compositions, but more to deal with exponents. This expression e raised to the x to the fifth power, just a little side note here, e to the x to the fifth power is what we're talking about. That is not the same as e to the x and then raised to the fifth power. Notice this is take x, raise it to the fifth power. That number becomes the exponent on e. So for instance, if x was 2, right, let's say x was 2, that would be 2 to the fifth, which is 32. We do that first. You'd have e to the 32nd power, which is a huge number. If you use your calculator and do e to the 32nd power, you get a huge number. Here, right, this would be e squared and then to the fifth power. Well, remember, when we're raising an exponent to another exponent, what do we do with these exponents? We multiply them. So this is e to the 5x, which is not the same as e to the x to the fifth. X to the fifth is not the same as 5x. 5x you can think of as x plus x plus x plus x plus x, right? 5x's, which is the same as e to the x times 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 e to the x, right? Because again, when we're multiplying like bases, we do what with these exponents? We add them, right? That's what we have with e to the x to the fifth power. That's what this is. So this is e to x to the fifth. That's e to the x times x times x times x, right? 5 times. Which you want to think about that. That's e to the x raised to the x, then raised to the x, then raised to the x, then raised to the x again. So just sort of different patterns there, but very common problems algebraically when you're simplifying expressions. You don't want to get confused. Okay, just a little side note there. All right, let's take a look at another related issue, finding the domain of functions, because sometimes in the homework for section 1.3, they'll ask you for the domain for the composition. So I just want to review that real quick. So for this first function, what's the domain? Domain is all the values of x for which we get a real number output. And you can see a problem when we're dividing by x squared plus 5x minus 6. If there's any value of x that makes that denominator 0, we've got a problem, right? Division by 0 is going to result in an undefined operation. It's not going to be a real number output. So any value of x that makes the denominator 0. So when is that denominator 0? Well, notice I can factor, right, x squared plus 5x minus 6 this way. And that means when x is -6 or 1, then the denominator will be 0. So I want to exclude those values. The way you would write the domain, therefore, could be this way in what we call set builder notation. We use curly braces to denote the values in the set, and this is all values x. This bar right here in mathematics, if you see that, means such that or given, and then there's some condition afterwards, and the condition being x is not equal to -6 or 1. In other words, x can be any real number except -6 and 1, and we can get a real number output to the function f. If you use interval notation, you just do everything less than -6, everything between -6 and 1, everything greater than 1. You can write it that way as well. Okay, so there's the domain for that function. What's the domain for this function? The square root of 3x plus 7 is the rule for the function g. Well, I cannot take the square root of a negative number and get a real output. So we're only looking for real outputs, real valued functions. And so I want 3x plus 7 to be greater than or equal to 0. Right? I don't want it to be a negative number. It can be 0. Square root of 0 is 0. I can do that, but not a negative number. So this is just solve this linear inequality, right? Subtract 7 from both sides, divide by 3, and we get x is greater than or equal to -7/3. So in interval notation, notice the bracket because we include -7/3. There's the domain, anything greater than or equal to -7/3. What about number 3 here? Well, again, I've got division by the square root of 1 minus 7x. Well, remember, I can't divide by 0, so 1 minus 7x can't be 0, but also 1 minus 7x, since I'm taking the square root, has to be what? Greater than or equal to 0, except it can't be 0 because now we're dividing by this expression. So basically 1 minus 7x has to be greater than 0. So up here we had greater than or equal to 0. Here we have to be explicitly greater than 0 because we're dividing by this, so we can't be 0. So here I solve for x, again, a linear inequality. I subtract 1 from both sides, and then I divide by -7. Remember what happens when I divide or multiply an inequality, a linear inequality, by a negative number? That will change the direction of this inequality, right, from greater than to less than. -1 divided by -7 is +1/7. So the domain is everything less than 1/7, which we can write that way. So anything less than 1/7 would be in the domain of the function. Again, domain being the values for which we get a real output to the function. The last one has ln. What's ln? That's log base e, right? That's the natural log. Remember, a logarithm is nothing more than an exponent. And so the important thing here is you have to remember that for any log function, the input has to be a positive number. The input has to be a positive number. And so x squared minus 16 has to be greater than 0. This is not a linear inequality. I can't just say add 16 and then take the square root, right? We've got to factor this and find out when it's 0. Of course, x squared minus 16 is easy to factor, difference of squares, and it's 0 when x is -4 or 4. Okay, but x squared minus 16, if I pick a number in between -4 and 4, like say 0, if I plug in 0, I get 0 minus 16, it's -16, and it's negative. It means this x squared minus 16 is negative for any value between -4 and 4. For any value greater than 4, like if I plug in 5 squared is 25 minus 16, that's a +9. So it's positive for that value. Similarly, if I plug in -5 squared, I get, again, 25 minus 16, which is positive. So that means it's going to be positive, and that's what we want. We want it to be positive for any value of x less than -4 or what? Greater than +4. So basically, we're excluding everything from -4 to 4 in the domain of this particular function. Okay, there's the function down there. So the domain of this function is this right here. So I hope that's a quick review of domains for you. There's certainly more that could be said again, but I just want to do one more problem, and that is, given these two functions, find their compositions, f circle g and g circle f, and then determine their domains as well. So notice, first of all, the domain for the function g of x is a polynomial function. Domain's all real numbers, right? I'm never dividing by 0 or taking a square root. F, since I'm taking the square root of x, x has to be greater than or equal to 0. So the domain is everything greater than or equal to 0. Let's find f circle g of x. Here it is, f of g of x. Again, g of x is x to the 5th plus 7. And I'm going to plug that into the function f. So I'm just going to take the square root of it. Okay. So remember, in this case, what we're plugging in, x to the 5th plus 7, that function originally, I can plug anything into the function g of x, right? So I don't have to worry about anything there, but whatever I'm plugging in to the function f has to be what? Greater than 0. So x to the 5th plus 7 must be greater than or equal to 0. And we can even see that in this rule right here, because clearly, if I'm taking the square root of x to the 5th plus 7, it has to be greater than or equal to 0. Now, again, this is a nonlinear inequality. I can't just subtract 7 and then take what the 5th root, which would be what I would need to undo x to the 5th. I can solve that equation that way, though. X to the 5th plus 7, when is that equal to 0? Well, I can subtract 7, and then I can take the 5th root. Now, the 5th root of -7 can be written as -7 to the 1/5. That's a real number. You can take an odd root of a negative number. This is, the 5th root of -7 is the number you multiply by itself 7 times, and you get -7. So obviously it has to be a negative number since it has an odd number of factors. You can actually go in your calculator and even approximate this. I did this already, -7 to the 1/5, and you get about -1.476 is what I said about. Okay, so that's when this thing is 0. So if I check x to the 5th plus 7, I want to know when it's greater than or equal to 0. Well, if I plug anything bigger than -1.476, like try 0. 0 is bigger than that number, right? If I plug in 0, 0 to the 5th plus 7 just gives me 7, positive. So everything's positive. Anything less than the 5th root of -7 will give you a negative answer. So for instance, something less than -1.476 is -2. If I plug in -2, I get -32 plus 7, which is -25. And so it's going to be greater than or equal to 0 for include that 5th root of -7 to infinity. It's real important in the homework, especially in Achieve or whatever the homework is you're using online. They'll often ask for exact values, right? So they don't want you to use this approximation. They want you to write it this way. Now, sometimes they'll say, approximate, and they'll tell you how many decimal places to do, and you can do it in that case. Be careful about your brackets and parentheses and where you put that infinity symbol for the unbounded interval in this case. If we go in the other direction and find g circle f of x, that's g of f of x. Again, f of x is the square root of x. So what is g of the square root of x? Remember, g was x to the 5th plus 7. So I'm going to replace x with the square root of x. So I get the square root of x to the 5th plus 7. Now you can rewrite this a little bit more compactly. Remember, the square root of x is x to the 1/2 power, and x to the 1/2, and then to the 5th, I multiply 1/2 times 5, I get 5/2. Right? X to the 5/2 power plus 1 plus 7. Right? This indeed you could write as what the square root of x to the 5th power plus 7. It can also be written as x to the 5th and then take the square root plus 7. You can interchange those operations there. But a lot of times this is the more preferable way to write it, at least for me, for sure. But just anytime you're giving an answer, make sure you're clear about the format it should be in. But this is fine right here. What's the domain? Well, remember, we started with the square root function, so I have to plug in any value that's greater than or equal to 0. The output to g of x, whatever it is, it will go into the function, the output to f of x will go into the function g, because g's domain, remember, was all real numbers. So the only restriction is where we start with the function f. And you can see that here too, because, right, again, we're taking the square root of x here, and we need to make sure that the input, therefore, is greater than or equal to 0. Okay, so that is just a fast and furious review. If you need more help with this, please let me know. and we can talk about it. But this is hopefully a refresher on, in general, compositions of functions.